Well, good afternoon, and thank you for coming to my talk today. My name is Chad Middleton. I'm a professor of physics here at Colorado Mesa University. And what I want to talk to you today about is about planetary orbits on two-dimensional surfaces. Now, namely, what am I talking about? What I'm talking about is the motion of marbles effectively on a two-dimensional surface. So I know what you're thinking. Who cares? Well, to answer this question, give me a few minutes to describe gravity as we understand it today. Isaac Newton, in his formulation of his universal law of gravitation, describes gravity as the force of one massive object acting on another. This law of gravitation, which lived from about the late 1600s to the early 20th century, remained unchallenged until the beginning of the 20th century. In addition to Isaac Newton's theory of gravitation as being a force of one massive object on another, being highly successful in being able to describe why an apple falls to the earth, it also was able to describe quite accurately the motion of the planets in the night sky. At the beginning of the 20th century, a physicist by the name of Albert Einstein came along. And Albert Einstein showed that Isaac Newton's theory of gravitation, where it describes gravity as a force of one object on another, is an approximation to a more fundamental underlying theory of gravity. This theory of gravitation is called Einstein's theory of general relativity. Einstein's theory of general relativity describes gravity not as a force of one object on another, but rather due to the warping of space and time, due to the presence of matter and energy. Now I know what you're thinking. How can I possibly imagine in my mind a warping of four-dimensional space and time due to matter and energy? So what is often employed by physicists in trying to understand conceptually as what is going on is to think in terms of an analogy. And this analogy is going to be that of a two-dimensional surface. So imagine a two-dimensional surface stretched taut across the room. Perhaps this is a rubber sheet or maybe a spandex fabric. And this two-dimensional surface is going to be an analogy representing four-dimensional space-time. Now, if I take a marble and I roll this marble across that surface, that marble will in fact roll at a constant speed at a straight line. But if I now take a massive object such as a bowling ball and first place that on top of the surface, and I repeat my thought experiment again, what will I find? Well, as the marble is far from that central object, that marble will move in a straight line at a constant speed. But as that marble starts to approach that massive object, you will find that its straight line path starts to deviate. The reason why this straight line path starts to deviate is due to the fact that the space in which it resides is actually curved. And it's curved due to this massive object. Now, you can imagine under the right initial conditions, if I roll the marble just right, I could in fact get a marble to orbit around the central mass, pictured on the screen behind me. Isaac Newton would say, well, the reason why the marble does the orbiting around that central mass is due to a force of gravity. This object is attracted to that central mass. But Albert Einstein's theory of general relativity would say that that is not what's going on. Einstein's theory of general relativity would say that the reason why the marble moves the way in which it does is not due to a force, but due to the fact that the space in which it exists is in fact curved or warped due to this massive object. This is our current understanding of gravity today. Einstein's theory of general relativity, which is 100 years old as of this past November, has been tested several times, and it has also gave predictions to exotic creatures, including neutron stars and black holes. And it has also made a prediction, a theory of study called Big Bang cosmology, which describes the time evolution of our universe as a whole, a dynamical system. So, my area of expertise is in Einstein's theory of general relativity, and I've studied this extensively over the years, and I've written papers on cosmology and on black hole physics. But a few years ago, I started to get interested in actually the analogy itself. How good does this analogy of a marble rolling on a warped surface actually do in describing the planetary motions that we see? And that's what I've studied, is the physics of this analogy. Does this spandex fabric that's warped by a massive object then give rise to a marble orbit to have the characteristics of, well, the planets? And the answer is no, it does not. So what I've been interested in the last 4 years ago or so is to ask the question, is there in fact some type of a two-dimensional surface where I could take a marble and roll it on this surface and give rise to orbits on this surface? And is there a surface that could generate marble orbits whose characteristics would be that of the planets? This is the question I wish to answer today. This surface that you see on the screen behind me, if you've ever been to a science museum, for example, you may have seen one of these surfaces where you can actually roll a marble on these surfaces, or you can roll a coin on this surface, and this is supposed to mimic what the planetary motions look like. The surface that you would see in one of those museums would in fact take this shape. So does this shape in fact produce orbits whose characteristics are that of the planets? And the answer is no, it does not. So what is this surface? Well, in order to answer that, when I say I want to be able to have a surface which has particle orbits or marble orbits on this sky, which precisely mimic those of the planetary orbits, what I mean is that I'm looking for a surface which will give rise to orbits where these orbits will in fact obey Kepler's 3 laws of planetary motion. Johannes Kepler was an astronomer about 400 years ago, and what he did was he analyzed the data that he had available to him. And what he found, the data being the positions of the planets in the night sky, and what he found was that there are 3 laws that describe these motions, and these are known as Kepler's 3 laws. The universe we live in is a mathematical universe. Our laws obey mathematical formulas, and these 3 applying to planetary motion are called Kepler's 3 laws. The first of the 3 Kepler's laws has to do with the shape of the orbit itself. And Kepler's first law says that the planets move in elliptical orbits. You'll see on the screen behind me 3 different types of curves. And if you look at the green curve, this would correspond to a curve of an elliptical orbit. Notice if I have a planet that orbited around following this green curve, when it got back, when it went through one full revolution, notice that it would in fact repeat that same motion on the next iteration. This is an elliptical orbit. Whereas, for example, some object that's following along on the blue curve or on the red curve would not be following an elliptical orbit. So Kepler's first law describes the shape of the orbit. Kepler's second law effectively is a statement of conservation of angular momentum, which says that as the planets orbit about the sun, well, the angular momentum of that system is, in fact, conserved. Now, it turns out for any 2-dimensional surface that we're talking about, Kepler's second law is generically obeyed. So this one's not so relevant to the work that I did. The last equation, or the last law is called Kepler's third law, and this is the only law that I can't state without a mathematical formula. What you'll see in Kepler's third law involves T, capital T is the period, the time it takes a planet to orbit around the sun. And R corresponds to the average separation distance between the planet and the sun. Kepler's third law gives rise to a relationship between this period and this average distance. Namely, the period squared is proportional to the radius cubed. These are Kepler's 3 laws of motion, and these describe not only the motion of the planets around the sun, but it turns out that any object that's orbiting around another massive object will in fact obey Kepler's 3 laws, so long as that central mass is large compared to the orbiting body. So, is there in fact a surface that I can roll a marble on that surface and have that orbit have the same orbital characteristics as the planets? And the answer is sort of. Let me tell you what I mean. On the screen behind me, you'll see 3, in fact, different surfaces, and I've cut away the central section so you can see what they look like. Each of these 3 surfaces will, in fact, if I take a marble and roll it on any of these 3 surfaces, I will find that the orbit will, in fact, obey Kepler's first law, the fact that this marble will move in an elliptical orbit, so long as it is circular-like. Kepler's second law is, of course, obeyed for any surface, generically speaking, so this one is obviously obeyed. And then the question is, what about Kepler's third law? If I have a marble that rolls on one of these 3 surfaces, and the way I can think of these 3 surfaces, if you look closely, the middle surface is an inverted cone. I can think of this as having 0 curvature, if you will. The outer surface I can say has positive curvature, and the inner surface has negative curvature. So, if I have a marble that's orbiting on any of these 3 surfaces, Kepler's first and second law is obeyed so long as those orbits are circular-like. How about Kepler's third law? Well, the outer surface, which I said corresponds to having positive curvature, what I will find is that if I have a marble that's orbiting on this surface, and that orbit is circular-like, then that marble will in fact obey Kepler's 3 laws. So what I want to leave you with is this. If you ever find yourself in a science museum and you see one of these surfaces like I showed earlier on, and you could have the opportunity to roll marbles on that guy or a coin, I want you to think to yourself, if that surface was replaced with the surface shown here, then what I would be witnessing is effectively seeing a marble trace out, well, a path taken by the planets around our sun that effectively is the same. Thank you very much.